welcome back. Here we are again talking about the Math64 library. You probably missed a few of these. So the latest edition is we're talking about, or we've just really got working a couple of different data types. So these are vector 2 and vector 3, and there's a vector 4 type there as well. But at the moment, I'm only really focusing on vector 2. And once that feels okay, the other two will be supported as well. I've just got to add the back-end code for it. So we'll run our standard PB example, which is running the library in the background in debug mode. I've got our error status over here, which is no compilation errors. And this is our code. So we've got a bunch of normal float variables declared using the var keyword. I might swap that to dim so people feel more comfortable with that, but at the moment, yeah, whatever. And so we've got variable A, B, C, D, and E. These are 64-bit floats. There's no integer type, no float 32 type, at least at this point anyway. Below that we've got two variables that are declared as vector 2. So we've got position and speed. So our position vector is going to have an x and y component, as you can see commented out below it. So the code goes on to do what you would expect. We've got position equals position plus speed, position equals position minus speed, position equals position times speed, and the final one is divide. Now I've had to set speed to 1, otherwise if I run the thing it'll get a divide by 0. Let's page down. Our variable table here is showing the state of the script after it's compiled. We've got our 5 variables up the top. A, B, C, D, E, and E is it? Yep. Variable number 5 is our position vector. Has a stack offset of 5. And then vector, the speed is also a vector 2, and it has a stack offset of 7. So it has. So really, what we're doing is that position has 2 local variables. You can think of them as x and y. They're just structures. In PB land, we call them types. We have one temporary vector, which is being used during these operations that below. So the bytecode is produced. We've got add vector, as you would expect, so we're adding vectors up the top there. And we've got a copy of the result. Now this is just a bit of slop at the moment because our phrasing needs to be updated a little bit to catch this occurrence. So we've got 4 instructions there we don't actually need in the long run. But anyway, so we've got an add of our vector 2's, we're doing a subtraction of our vector 2's, a multiplication of them, a division, and then we're ending pretty much. And this copy here is just moving. When we do an addition, we're adding our position and our speed together. We're storing it at a temp. Then the next instruction is copying that temp into the target variable, which is position. So since position is the last used variable in the expression, we can actually shortcut that, which is what we normally do in PB anyway. It gets rid of these kind of temp instructions that just move some data from an expression into the answer, into the result. Long-winded? Yep, long-winded today. Let's hit run. So we've got, not too bad, 96 million instructions per second. Again, don't get too excited by that stuff, but we are doing effectively, for every instruction we're running, we're doing double that. we're adding x and y's together. If it's an addition, we're subtracting those out too as well. So I think what we're getting to here is, if we can do, say, a million Math64 instructions in a reasonable time, in a couple of milliseconds, for example, you could shift a whole bunch of your math operations out into the script. And not just trivial, occasional things either. You could do some of the heavier math outside of that, if we can get the vector stuff to work, obviously. Let's not put the cart before the horse. Now, of course, what we need as well is we need things like, we'll get a normal vector, cross product, dot product, whatever else I can think of off the top of my head to implement internally. And I think if we have those internally as well, it would even, it would boost your performance even more by doing those things. That's assuming you're using vectors in your everyday life. Yeah, and you probably are, because even though that PV functions, often require you to supply the x and y coordinates of things, we're still doing vector operations when we do basic trig. It's all the same stuff in a different representation, pretty much. All right, so that's pretty cool. I'm pretty happy with that. That's working. I had a bit of a problem with this on Saturday, and the main problem was just that the PB side of this code here, which was displaying this information back to us while I'm debugging this thing, really. To say it's stable would be overly kind. Certainly, I wouldn't expect it to work, and hasn't been tested that robustly. But this information here is done on the PB side of the equation. So we're displaying this information out in a bit of code in our PlayBASIC program. For example, the code that does the code that displays the bytecode has to disassemble the bytecode that was compiled by the back end. So it just has a select case statement that runs through, and it knows the instruction set and decodes them as it expects. It backing into something that makes sense in terms of on screen, rather than a bunch of numbers. That's all. The problem is that one side of the equation one side of the library was not as up to date as the other side, and there was a rounding problem in C. It likes to round structures occasionally, which is kind of annoying. The library itself has kind of grown a fair bit. We've got our new instructions sit inside the runtime. In PV terms, we're just having a select case statement. That's all the stuff is. That's all it is. Some of the trickery, I guess, comes from picking out when to have simple instructions and when to have complicated instructions. And that's always an argument that goes through your head, Should I have this instruction do 5 things or just do 1? So this is our vector instructions here. So it's mostly setup code. Don't be too confused by it. We're grabbing our that should be target vector actually, grabbing our left term, grabbing a pointer to the right term, and doing a stupid addition. That's it. That's all there is to it. Stepping forward in the bytecode to the next instruction. Off we go. Subtraction's the same, division's the same, all the same crap. I've got a bit of stuff already in it. Mostly square root, arctan, tan, polar x coordinate stuff. Cos, sine, ceiling, floor, absolute. Yeah, so we've got a few functions built in. We'll need some more functions to make the vector implementation feel a bit nicer. At the moment, we can't do things like, you look at our vector source code here, for example, at the moment we can't actually set the vector, which is a glaring omission. Can't just go position equals x 100 or something. Position, y equals 200. The Fraser doesn't actually support this kind of expression at the moment. It can read from them within an expression, but it can't do an implicit write like that. We probably should have something like, position equals, maybe some square brackets or something. Make people feel all warm and fuzzy. Maybe we'll have that there as well for to handle doing. So that would be the same as what the code is above here, by the way, if you're a bit lost. It's just a shortcut for that same thing. Who knows? If it's, it might be worth adding that stuff, it might not be worth adding it. That's a pretty simple code. If you want these things to be vector 3, just swap it to vector 3. This will all compile the same, but it wouldn't generate code at the moment because there's nothing in the back end of this that does actually. There's no instructions in the runtime to actually do those operations. If you catch my drift. So for a little project, it's blown out a little bit. It's it's got a bit of extra crap there in the back of it, but I don't know. Looking at probably 6,000 lines of code and probably another 500 lines of declarations. All the same kind of stuff. A lot of it's sort of mundane boilerplate stuff, but I'll get over it. Right. So what I'll try and do is I'll try and get a way of setting the vectors up, implement it, even if it's just a little hack, like a set vector function for the time being. Tomorrow, I guess, when I post this video, and I'll just post it however it is. You can just see the progression as we're going through. If you've got any ideas about what kind of functions we might need, if you've got some usages tucked away out there, or a way we might, with vectors in particular, if you have a script where we can allow it to be inside the script and then execute batches of the same thing, that would be really neat, because it would mean PB could call the script engine could execute and do a bunch of work, and then once it's done, it just returns control back to PB, and we copy the data back out. That's probably the most efficient way of doing it. So for things like particles, that kind of stuff, that would be very good, or better, I would imagine. Anyway, I'll leave you to it. Thanks for watching, and I'll see you next time.